Hello everyone. We will now begin our lecture on section 4.2, which is on the place value or positional value numeration systems. Now we started our discussion on number systems with section 4.1, where we discussed some of the ancient civilization number numeric systems, starting with the Egyptian system, which was based on the addition principle, solely on the addition principle. And then we went on to discussing the Roman numeration system, which not only use the addition principle but also use the subtraction and the multiplication principles. Now we will go on to discussing another type of numeration system, which is the place value or positional value system. Now the number system, which is used widely uh, today, is the Hindu-Arabic numeral system, and that is based on the place value system. What happens in the place value system, to give you a short introduction before we dive into the details, is that a number, all right, a number consists of digits, and each digit from right to the left has a positional value. All right, it has a positional value. So if we have a 3-digit number, then the digit on the extreme right is the units. All right, it's the units, also referred to as the units place. And then 2, which is the number or the digit to the second digit from the right, that's the tens position. And then the third one from the right, this 1, would be the hundreds position. So what we do is we multiply each of these digits, individual digits, by the positions, and this is a base 10 system. All right, we can have different bases, but in the Hindu Arabic numeral system, we use the base 10 principle, the base 10 numeration. And then once we multiply each of these digits by their place value, we go ahead and add the value. So we will go through a lot more examples. It was just meant to be a brief introduction into what the place value or positional value system is. So as part of the place value numeration system, we will first try to understand what the place value numeration system is about, and then we will talk about the Babylonian and the Mayan numerals and how the positional values, the place value system works or worked for their number system. So let's try to understand what the place value numeration system is. In the place value numeration system, the value of the symbol, or the value of the number, depends on its position in the representation of the number. It is the most common type of numeration system in the world today, which is based on the Hindu-Arabic numeration system. There are other place value systems also, but the one that is used widely throughout the world today is the Hindu-Arabic numeration system. And the main reason for that is because it has a value for 0 to represent 0 to represent nothing. And it says here this is used in the United States, but it's not just the United States where it's used, but it's used throughout the world, almost throughout the modern world. So let's try to understand how the place value numeration system works. All right, so they have given us an explanation here, so I will just read through it first, but it won't mean much just reading through it until we work through an example. So I'm going to explain later on with a specific example how this system is going to work. All right. So here it says a true positional value system requires a base, and I'm going to explain what they mean by base, and a set of symbols, including a symbol for 0 and 1 for each counting number less than the base. The most common place value system is the base 10 system, which the Hindu-Arabic numeral system uses. The Hindu-Arabic numeral system is a base 10 system. It's also called the decimal number system, and that is the system which is widely used throughout the world. All right, so I will use an example of the Hindu-Arabic numeral system, which is based on the base 10 system. Now, there are other base systems as well, like base 2, base 16, and so on. However, we will start with the base 10 system because it's easier to understand, because that's what we use to come up with the numeric value of numbers as we know today. All right. So over here, it says a true positional value system requires a base and a set of symbols. So what are the numeric symbols that we have in our system? They are 1. They start from 1 because they are the counting numbers. Counting numbers always start from 1. All right. So 1, 2, 3. Let me write these down. 4, 5, 6, 7, 8, and 9. So we have a symbol for each counting number, which should be less than the base. All right. So if we are using a base 10 system, then our symbols should end at a value less than whatever the base is. All right, so base 10 system. And then we should also have a symbol to represent 0. 0 means nothing. All right, so we have a number for 0, and we'll keep it separate because 0 is not a part of the counting number. Now, if we want to represent a number, let's say a 3-digit number, for instance, what I'm going to do here is a 3-digit number will need 3 symbols, correct? It'll need 3 symbols. So I'm going to put 3 dashes here as placeholders for the 3 digits. These can be any digit. All right. So we'll put a digit in each of these numbers depending on what number we want to represent. So let's say we want to represent the number 7, 5, and 6. Now what happens is, to come up with the numeric value of these 3 digits put together, we start from the extreme right hand side digit. All right. So the extreme right position of this number has a positional value of ones. All right, so it's actually ones. Then the second place from the right, all right, the second position from the right has a place value. We call it tens. The tens place, the ones place is the extreme right hand side digit. Then the next one to the left is the tens, and this is all S. All right, I'm just trying to indicate this is the ones position, this is tens position, and then the third one is the hundreds position. And if there are more digits, then it keeps increasing in multiples of 10, so it'll be the 1000s position, and then if there's another one, that will be the 10,000s position, then the 100,000s position, millions, billions, and it keeps going like that. All right, so the place values increase as we move from the right to the left, all right. Now these 1, 10, 100, 1000, 10,000, and so on can be represented as or in exponent form with base 10. Because we are increasing in multiples of 10, we can write these values. Now the extreme right hand value is 10 to the power 0. If you recall from your knowledge of algebra, any number raised to the power 0 is always 1, correct? So the extreme, the ones position can be written as 10 to the power 0. Then the second position from the right is 10 to the power 1. All right, I'm sorry. Let me just change this. 10 to the power 1. And we go going increasing the exponent by 1. So the hundreds place is 10 squared. Then we have 10 cubed. Then we'll have 10 to the fourth. 10 to the fifth. So you see what they mean by base. All right, so we use a base 10. If we were working with a base 2 system, then it would be 2 would be the base. So 2 to the power 0, 2 to the power 1, 2 to the power 2, 3, like that. All right, so we're just talking about base 10. So our bases are 10 in exponent form. And the extreme right hand exponent is 0. Again, I'm repeating this. Anything raised to the power 0 is 1, and that's what makes it the ones place. All right. 10 to the power 1 is tens place, hundreds place, and so on. Now to calculate the numeric value of the number 756, what we do is we multiply each digit by its positional value. So this is 7 times 100. All right, so we are going to do the calculation like this. 7 times 100 plus 5, here, 5 times 10. All right, so 5 times 10 plus 5 times 10 plus 6 times 1. 6 times, 6 times 1. All right, and then we multiply this out, and then we will end up adding. All right, so it'll be 700 plus 50 plus 6 for a value of 756. All right, so that is how we apply the place value numeration system. All right, so each digit in a number in the place value system, each digit is associated with a positional value, and based on its position, we multiply each digit by its place value, and then we sum them up. All right, we'll go through some more examples of this in the later slides. Now the next few slides go through the same thing that we already covered in our previous slide, but I will run through them anyway, just as reinforcement. So it says here the Hindu-Arabic system. They have laid out the digits in the Hindu-Arabic system. The digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. But the counting digits are start from 1 all the way to 9, and 0 is used as to represent this symbol for 0 is used to represent 0. All right, which means nothing. Positions in the Hindu-Arabic system, the positional values or place values are from the right to the left in increasing exponents. All right, 1, and again, as I said before, 1 is really 10 to the power 0. All right, so even though it says 1, it can be represented in base 10 as 10 to the power 0. Then we have 10 to the 1, and then 10 to the 2, 10 to the power 3, 10 to the power 4, 10 to the power 5, and we keep increasing the exponents as we move to the left. And those represent the place values, the value of each position in the system where the digit will be placed. All right, so the digit, if it's placed in this position, which is the third position from the right, then it will have a place value of whatever the digit is multiplied by 10 squared, which is 100. So if the digit here is a 7, then it's 7 multiplied by 10 squared is 700. All right, so that a digit placed here will have a value of 100 times whatever that digit is based on this positional system. So again, to repeat what we already said, the expanded form, to evaluate a numeral in this system, first multiply the first digit on the right by 1 or 10 to the power 0, and then multiply the second digit from the right by base 10 to the power 1, and then multiply the third digit from the right by 10 squared, and so on. All right. In general, we multiply the digit n places from the right by 10 to the power n minus 1 to show a number in expanded form. So now we will go through an example of writing a Hindu Arabic numeral in expanded form. All right. So here the number given to us is 1234. So using the place value system, we take the 4, which is the digit on the extreme right, and multiply it by its positional value of 1 or 10 to the power 0. And then plus we take the second digit from the right, all right, and that the positional value of that is 10, so 3 times 10, and plus 2 times 10 squared, plus 1 times 10 cubed, so that's 1 times 1000, plus 2 times 100, plus 3 times 10, plus 4 for a value of 1234. All right. Now let's talk about one of the oldest numeral system, which was kind of similar to the place value system. But if you recall, the place value system said that there had to be a value, or rather a numeral, to represent 0, correct? It said that it needed a base, it needed symbols for the counting numbers, and a symbol to represent 0. In the Babylonian numerals, there was no 0. All right, Hindu Arabic, the Hindu system was the first one to come up with a symbol for 0 to recognize that even if there was nothing, it still need to be represented as a number. However, some of the other ancient civilizations did not have a place or symbol for 0. But it followed a few of the other principles of the place value system. So let's go through this. So Babylonian numerals is one of the oldest known numeration system that represented a place value system. It was developed in 2500 BC, and its place value system was based on base 60, all right, not base 10 like in the Hindu Arabic system. It had base 60, also called the sexagesimal system, just like we have the decimal system for base 10. For base 60, we refer to that as a sexagesimal system. Now, it's not a true place value system. Why? Because it lacked a symbol for 0. The lack of a symbol for 0 led to a great deal of ambiguity and confusion, but let's know how they worked around that and came up with their own numeral system. Now, the Babylonian numerals are just 2 numerals, all right? So one we have, the first one here is like a straight line, all right, with its top broader than the bottom, all right? And then we have a left pointing arrow, so to speak. So the first numeral, which is like a straight line, represents the number 1. Then this left pointing arrow has a numeric value of 10. So using these two symbols, they came up with a number system with using the positional values. The extreme right digit had a value of 1, then 60, or rather 60 to the 1, 60 squared, 60 cubed, and so on. Now, a few other rules in the Babylonian numeric system was that a gap was left between characters to distinguish placed values. In other words, each digit was separated by a space. All right, so we could have uh, the first digit represented by two staffs like this. All right, something like this. And then we could have, and both these two staffs represented the first digit. All right, and then we could have something like this, this, and this. All right, this. All right, and there was a space, a gap in between the two, and all these three represented the second digit. All right, so we had here, the way to do the calculation is we would first calculate the value of these two digits put together. So if each of these uh, numerals represent 1, so 1 plus 1 represents 2. All right, this represents 2, and these left pointing arrows represent 10 each, right? So 10 plus 10 plus 1 represents 21, right? So the way we would find its numeric value is 2 times 1 for the first first set of digits, and then it's 21 times multiplied by 60. All right, and then we end up adding them. And then if there was another set of digits to the left, it would be multiplied by 60 raised to the power 2, then 60 raised to the power 3, and so on. All right, so let's see what we get here. It says from right to left, the sum of the first group of numerals is multiplied by 1. All right, and then the sum of the second group is multiplied by 60. The sum of the third group is multiplied by 60 squared, and so on. All right, so that's how the Babylonian numeric system was. So let's go through this example of finding the numeric value using the Babylonian system, right? So it says here, these are the symbols given to us, and as you will note that I'm just trying to pull up my pen here. All right, so we have a set of symbols on the right side, and that's going to represent the digit on the right, and then there's a space which tells us there's another digit to the left. So we will first have to find the value of each of these digits and then multiply by their place values, right? So look at this. This is, we have on the right hand side 2 arrowheads and a staff, right? So each arrowhead has a value of 10, right? So it's 10, and then the second arrowhead is 10, and then we have a staff which has a value of 1. So 10 plus 10 plus 1, so the value of this digit on the right hand side is 21. Let's calculate the value of the next set of symbols to the left. So we have 1, 2, 3. We have 1, 2, 3 arrows, which would be 30. 10 plus 10 plus 10, 30, and 4 staffs. So 30 plus 4 would be 34, right? So it would be 10 plus 10 plus 10 plus 4 staffs. So 34. All right. And the place value for the 34, it's in the second position from the right. So it's going to be 60 raised to the power 1. The place value of the symbols or of the first digit represented by these symbols is 60 to the power 0, which is a 1. Any number raised to the power 0 is a 1, right? So let's see how we work through this problem, all right? How they worked through this problem in the PowerPoint slide. So let me pull up those. All right, so this is the solution coming up. So just as we said before, or we worked out here before, 10 plus 10 plus 10, and then 4 ones would make that 34, and for the right hand digit it's 10 plus 10 plus 1, like we worked uh, here, right, for the rightmost digit. And then 34 multiplied by 60 would be the value of the left digit, and 21 multiplied by 1. And again, why are we multiplying by 1? 1 is equivalent to 60. All right, this is equivalent to 60 to the power 0. This here, 60, is really 60 raised to the power 1. If there were more digits to the left, then it would be multiplied by 60 to the power 2, then 60 to the power 3, 60 to the power 4, and so on, right? So the final answer would be 2040, right? 34 times 60 evaluates to 2040, and 21 times 1 is 21 for a value of 2061. All right, so that is how we are going to calculate the values of a number, numeral, using the Babylonian system. Now we are going to learn how to convert a number in the Hindu-Arabic form to its corresponding Babylonian numeral. All right. So the way we go about it is using a process of division of the Hindu numeral by the place values of the Babylonian numeral. So let me review the place values in the Babylonian numeral. The digit on the extreme right hand side in the Babylonian system would have a place value of 60 raised to the power 0, which has a value of 1, correct? So it means 1. Then the next digit to its left would be 60 raised to the power 1. So that means it's 60. Any value raised to the power 1 is the value itself. So it's going to be 60. Then the digit on the third digit to the left would have a place value of 60 squared. So it's going to have a place value of 60 squared, which is, when you do 60 times 60, you will get a value of 3600. And then if we go another place to the left, the fourth digit from the left, then it's 60 raised to the power 3, which, when you multiply it out, is going to have a place value of 216,000, really. All right. So what we do now is we look at the Hindu value, right? The Hindu numeric value, which is 7223, and we will divide it by a value closest to 7223. All right, closest to 7223 without going over. It cannot be more than 7223, but it should be less than 7223, but as close as possible. So among these values here, 160, 3600, and 216,000, we see that 3600 is less than 7223, but it is also the value closest to it. 60 and 1 are also less than 7223, but it's not as close to 7223 as 3600 is. So we are going to go ahead and do this division here on the side. So it's going to be 7223 divided by 3600 is what we are going to divide 7223 by. So 3600 multiplied by 2 is 7200, and when we do the subtraction, this is just like any arithmetic division. When we subtract it, we get a remainder of 23. All right, so that tells us that uh, that 3600 goes into 7223 twice but leaves a remainder of 23. Now since we got this value 2 after we did the division of the 3600 position place value, all right, that is the third digit from the right, all right, so that means 2 is going to take the position of the third place from the right. All right, so we are going to end up with, for here, all right, in the Babylonian system, this is going to be 2 multiplied by 60 squared. Right, now we have to figure out the remaining units, or rather the remaining digits here. So we still have a remainder of 23. What we do now is we take the 23 and divide it by the next place value on the right of 60 squared. All right. So we started with 60 squared. We started the division with 60 squared for the next division, and we are dividing the remainder here. So the remainder, let's see if we can divide by the next place value to the right, which is 60. Now, 60 is greater than 23, correct? So that means we cannot divide 23 by 60. It tells us that the value of this digit here, the value of this digit here is going to be a 0, just because 60 goes to, let's do it this way, 60, when we try to divide 23 by 60, we will have a quotient of 0, right? And then 60 times 0 is 0, and we will now be left with a remainder of 23 again. All right, so this tells us that the second position, all right, is going to have 0 as its numeric value. All right, so it's going to be 0 times 60 raised to the power 1. So now we still have the remainder of 23, and we still have another position here, 60 raised to the power 0, which is the units place. We can divide 23 by this 1, correct? So that's what I'm going to do now. 23 divided by 60 raised to the power 0 is a 1. And what will we end up with? 1 times 23, and then is 23. And when we do the subtraction, we get a 0 as the remainder. All right, so we have 23 for the quotient. You take the 23 and then 60 times 0. All right, so how are we going to write that now in Babylonian numeral? All right, so it's going to be like this: 2 times 60 squared, right, plus 0 times 60 raised to the power 1 plus 23 times 60 raised to the power 0, right? So how do we represent 23? We can use 2 arrowheads, right? Each arrowhead has a value of 10. it represents the number 10. So 2 arrowheads followed by 3 staffs. All right, so we can just do this. 3 staffs. And that represents the extreme right hand digit. Now 0 times 60 is 0. So we have to leave a gap here. All right, as it is, we have to leave a space and then another space to represent this 0 here. All right, there's no Babylonian symbol to represent 0, so we just have to leave some extra spaces. All right, and then another space here for this plus here. So leave considerable space, and then 2 times 60 squared. All right, so 2 times 60 squared would be, we just have to represent the 2. So it's going to be 2 staffs. 2 staffs. Okay, so when you work this question out in the assignment, make sure that you leave enough space, and the best way to make sure that you have left adequate space is just represented by these dashed lines. All right, that would indicate space, space, space. All right, one space between the rightmost digit and the one next to it, and then another space to represent the 0, and then this space is to represent the gap between the second digit and the third digit to the left. All right, so now let's see how the PowerPoint has given the solution to us. All right, so just give me a minute. I'm going to erase this because the solution is going to appear over what I've written, so I need to erase this so we can read what is going to come up. All right, so here's the solution. It says here, divide 7223 by the largest positional value less than or equal to 7223, which in our case was 3600. All right, so they did that, and then when they did the division, they got the same quotient as we got here. So 2 remainder 23. So this was our remainder. Then let's see what they do in the next step. So they said we now have 2 groups of 3600. That means there are 2 3600s. Right? And that's why we wrote, if you recall, we wrote it as 2 times 60 squared. Correct? So in the next step, what do they do here? It says the next positional value is 60, but 23 is less than 60. So there are 0 groups of 60 with 23 units remaining, and that's what we found here. All right, so we took our remainder and we tried to divide it by the next positional value, which was a 60. Next to the right of 60 squared is what. Now this time we are going right, from left to right. All right. So here our remainder is still 23, and then in the next slide they will take us through the completion of this problem. All right, where we will see they divide the 23 by 1 and we'll get a remainder of 0. So this is how it's going to be eventually, the same as what we wrote. It's going to be 0 times 60. So the second digit is essentially going to be a 0. All right, 60 raised to the power 1, and plus it's going to be 23 times 60 raised to the power 0, which is a 1. All right, so let's see how they have continued with the solution in the next slide. So let's see what the final solution looks like. Right, so the way we go about here now is now write 7223 as follows. So they have written it as 2 times 60 squared plus 0 times 60 plus 23 plus 1. Actually, this should be 23 times 1. So this is a mistake here. It should be 23 multiplied by 1. All right. So the Babylonian numeration system does not contain a symbol for 0, so leave a larger blank space to indicate there are no 60s present in 7223. In other words, we are leaving 2 spaces, all right? And then finally, our answer is 2 staffs here, two arrowheads from right to left. We have 2 arrowheads with 3 staffs, which make 23. So 23 times 1. And then we have considerable space, 1 over for this digit, all right, and then again for this digit. So we actually have here 3 spaces, 1 here, 1 for 0 plus 60, and then this space here, and then 2 times 60 squared, and that's exactly the answer we obtained when we worked it out. All right, so this is how we will be converting from the Hindu-Arabic numeral to the Babylonian numeral. We will now go over the Mayan numeral system, and here we have the symbols of the Mayan system. Let's try to understand a little bit of the symbols. There are about 20 symbols out here from 0 through 19, and the corresponding Hindu numerals versus below here with dots and dashes, the Mayan numerals, right? But let's look at some pattern in the numerals so we can figure out, without having to refer to a table, what the values or the uh, numeral values of those symbols would be. All right. So we see 0 represented by these oval circles, and then 1 with 1 dot, 2 with 2 dots, 3 with 3 dots, 4 with 4 dots, and then 5 has a dash, right? To represent the symbol 5, there's a dash, and pretty soon we will see that there was a concept of multiples of 5 in the Mayan uh, system, right? So over here for 6, it's a dash and then a circle above. So 5 plus 1, 6, right? 7, for 7, it's 1 dash for 5 plus 2, plus 2. 8, same way, 5 plus 3. 9, 5 plus 4. And then 10, we have 2 dashes. For 11, 2 dashes and a dot, and so on. For 15, it's 3 dashes. So you can see they had some concept of multiples of 5. 5, 3 dashes, so 3 times 5 is 15. So that's how the whole uh, symbolic numeral system was set up. Right? Now, what about the place value? So let's bring that up here. All right, so the positional values in the Mayan system goes like this. 1 for the lowest digit, then we have here 1, and then the next place value is 20, and then we have 18 times 20, and then 18 times 20 squared, 18 times 20 cubed, 18 times 20 to the fourth. So that's how it will be going. All right. So again, the lowest unit, the units place, is going to be multiplied by 1. And then we have 20 raised to the power 1. Right. But then after that, it's 20 times 18. All right, so this is how the Mayan system is. So you have to remember that 120, but then from the third place it becomes 18 times 20, 18 times 20 square, 18 times 20 cubed, and so on. All right. Uh, so again, these are the corresponding values over here. 1 is 1, and then 20, and then 18 times 20 is 360. 18 times 20 squared, 7200. 18 times 20 cube, 144,000 is what we would multiply the fourth place digit by, and that's how it goes along, right? So let's learn a little more about the Mayan system in the following slides. Now, the representation of the Mayan numeral system was done somewhat differently than the Hindu system or the Babylonian system, right? So let's bring that up. The first important feature and the first important difference between the Hindu system and the Mayan system was that the numerals are written vertically. In our system, we would normally represent our numbers horizontally, and we saw it was the same in the Babylonian system as well. So in the Hindu system, a number like 253 would be written horizontally with 3, which is the units position, to the right, and then the next tens position would be to its left, and then the hundreds position would be to its left again. It was the same thing with the Babylonian system. So the digits were uh, would come in blocks, correct? However, they were all written horizontally with a space in between the two, between any digit, right? But it was represented horizontally. In the Mayan system, the numerals are written vertically, all right? So you will see the symbols appearing one below the other. It's going to appear one below the other. It's as if we are writing 253 as 253. All right, so that's how it's going to appear, the Mayan symbols, with the lowest units digit at the very bottom, and then we will be going up as the place values increase. All right, so it's like a bottom up configuration. Let's bring up the next. It says units position is at the bottom of the vertical placement. All right, so 3, which in this case is the units place, would be at the very bottom, and the numeral in the bottom row is multiplied by 1. All right, so it's going to be multiplied by 1, and then the numeral in the second row is multiplied by 20. So this one would be multiplied by 20, the 5. Numeral in the third row is multiplied by 18 times 20. So from the third row, we start multiplying by 18 times 20. 18 times 20 squared. 18 times 20 cube as we go up. All right. Fourth row multiplied by 18 times 20 squared, and that's how it's going to go. So we have to keep that in mind, that particular feature about the Mayan system in mind, that the digits are represented in a straight line vertically and not horizontally, that we have been familiar with so far. All right. So we will now go through the process of converting a Mayan numeral to its Hindu Arabic equivalent. All right. Now we already know that the Mayan numeral is configured in a vertical pattern, right? And the lowest digit appears at the bottom, and the place values increase as we go up from the bottom. So again, it's a bottom up configuration along the vertical line, right? Now, what were the place values that we learned? The lowest digit will have a place value. That means the bottom row will have a place value of 1. The one above, the row above, will have a place value of 20. But then from the third row, the pattern changes somewhat. It's 18 times 20 raised to the power 1. All right, and then the next one above would be 18 times 20 raised to the power 2. Then the one up, if there was another row above, if there were a fifth row, then it would be 18 times 20 cube, and that's how the pattern progresses. All right, let's try to read some of the values of the numerals. So we have 4 at the bottom, right? At the bottom row, we have 4 dots, and that represents 4. Then we have above that 2 elliptical circles. That represents what numeral? 0, right? So it's going to be a 0. And then we have a dash with 3 dots above, so that means 5. The dash represents 5 plus 3, 8. It's going to be the 8. And then we have 2 dots in the 4th row above, so it's 2. So to come up with the Hindu-Arabic equivalent, all we need to do is multiply 4 by its place value, which is a 1, and then 0 multiplied by 20, and then 8 multiplied by 18 times 20, which is going to be 360, and then 2 times 18 times 20 squared, which is going to be, this is also 7200. 18 times 20 is 360. All right, so we will do those place value multiplications, and at the end we have to add up the values of these digits, which will give us the Hindu-Arabic numeral equivalent. Now, in the next slide, they have gone through the steps. Let's look at that now. So here's the solution. Let's look at it first. Over here, we start from the bottom row, just like we said in the previous slide. We multiply the value of the symbol at the bottom by 1. All right, so 4 times 1 is 4, and then the one above is 0, right? These 2 elliptical circles represent 0. So 0 times 20 is 0, and then for the next row above, it's 8 times 18 times 20, which is 18 times 20 is 360. When we multiply that by 8, we get a value of 2880. And then we have the topmost row, which represents 2. So 2 times 18 times 20 squared gives us a value of 14,400. And then finally we have to add all these up for a value of 17,284. So that's how we are going to go about converting from the Mayan system to the Hindu-Arabic numeral system. We will now go through the process of converting a number in the Hindu-Arabic form to its Mayan equivalent. So the number given to us is 4025. Now the process to go about converting it to its Mayan equivalent is the process of division by the place values, and we use the same process when converting from the Hindu system to the Babylonian system previously. So it's going to be the same process, except that the place values are going to be different. So let me remind you a little bit about the place values of the Mayan numeral system. What was it? The first value, or the first digit rather, had a place value of 1, correct? And then the next one, again, the Mayan system, of course, the configuration of the digits are in a vertical structure with the lowest digit at the bottom, and then the place values increase as we go up from the bottom up. All right, so the place value of the number at the bottom would be 1. Then we have 20 for the next place value, and then the next higher place value is, however, 18 times 20 raised to the power 1, and then the next one is 18 times 20 squared, and it continues, right, as we go up the Mayan system. Now, so let me just write the equivalent number. So 1 is 1, then this is 20. Now 18 times 20 is 360, and 18 times 20 squared is 7,200. So when we go about converting it, we have to divide, right? So we have to divide 4025 by a value in this place value system, which is close to 4025 but does not go over. So we are going to divide 4025 by 360 because that's the value that is closest to 4025 but still less than that. All right, it's not going over 4025. So let's perform the division here. So 4025 divided by 360. Let's see what we get. 1 times 360 is 360. We subtract, we get 2, and then 425, and then 360 times 1 is 360 times 1 is 360. Again, subtract, and we are left with 5 and then 6, right? 65 is the remainder. So what this tells us is 360 goes into 4025 11 times with a remainder of 65. So we have 11,360. So this value 11 is going to go to this position, the third position, all right, of the place value system. And then we are left with 65. We have to keep going. 65 has to be divided this time by the number closest, by the place value number closest to it without going over. So we are going to divide 65 by 20 this time. So 65, let's use a different color maybe. So 65 divided by 20 is going to be 3, right? 3 to 6, 60, and then we are left with a remainder of 5. All right, so we have a remainder of 5. We have to keep going. So 5, this time we are going to divide by 1 because 1 is the number that is closest to 5 without going over. So 5 divided by 1, 5 is the quotient. 5 times 1 is 5. We have a remainder of 0 now, and we are done. All right. So 5 is going to be the value that goes in the units place, and 3 in the tens place, and then this one in the 360 place. Well, I shouldn't really be saying tens because that's the Hindu system, but it's 3 is going to be in the second position, and 11 is going to be in the third position, whose place value is 360. So how are we going to represent this in the Mayan system? We have to, of course, represent these numbers vertically, and the lowest one is going to be 5. So how do we write 5 here? In the Mayan system, 5 is just one dash, right? And then above it is the 20s place, right? The second place, let's put it that way. It's 3, correct? So how do we represent 3? As 3 dots, correct? And that goes right above it's the second top row. And then we have 11. How do we represent 11? 11 can be written as 2 dashed lines, 10, right? 5, 5 plus 1, correct? All right, so the Mayan equivalent of 4025 is going to look like this. Now let's see what the solution given here is. I'm going to erase some of this writing, and so we can see what comes up here. Just a second. The solution, it says divide 4025 by the largest positional value, place value, less than or equal to 4025. In our case, it was 360, and we did the division here, right? We came up with 11 360s with a remainder of 65, if you remember. And then they did the division here, 11 with remainder 65, and then there are 11 groups of 360. We got the same result. The next positional value is 20, correct? So we divided 65 by 20, which is the next positional value. And then what did we find? Let's see. We did a 65 divided by 20 is 3 with remainder 5, exactly what we worked here. And then finally 3 groups of 20 with 5 units remaining, and that's what we did here, right? So let's go on to the next slide and see how their Mayan numeral equivalent looks like for 4025. It should match with what we got. So let's look at the end result of converting 4025 to the Mayan system. See what comes up. We have 11 times 360, 3 times 20, 3 times 20 plus 5 times 1. So 11 times 360, 3 times plus 3 times 20 plus 5 times 1. All right, so let me get everything out here. So to represent 5 times 1, again, we have to do the arrangement vertically. 5 times 1 is 1 horizontal bar. Then 3 times 20, 3 dots. All right, so we are just representing these values here, right? 3, 5, 11. You don't have to represent the 20 and 360. So for 11, we represent it as 2 5s, so 2 dash bar and a dot. That's 11. So now we have the Mayan equivalent of 4025. All right, so this is how we are going to go about converting from the Hindu-Arabic system to the Mayan system.